Welcome to The Explainer. Today, we're kicking off part one of a brand new historical series exploring the origins of the Hierarchical Script-Database, or HSDB for short. We're going to dive right into the exact moment that sparked a complete paradigm shift in software architecture. We are talking about this absolutely crucial concept called structural isomorphism and how it fundamentally reimagined the relationship between your data and your code. But before we get into the weeds, I want you to really chew on a fundamental question as we trace this mind-bending path. We're going from a seemingly simple summer email back in 2020 all the way down to the complex fractal mathematics that are actively redefining computation today. So think about this. What actually happens when the boundary between what a system knows and what a system does completely vanishes? All right, here's our roadmap for today's explainer. We'll start with the nouns and verbs, move into the June 2020 Spark, define structural isomorphism, break down the math of isomorphism, and finish up with some echoes from the past. Let's get into it. Part 1. The nouns and verbs. Let's just quickly set the stage with the fundamental friction that has plagued software developers for decades. So traditionally, systems enforce this rigid, honestly almost impenetrable boundary. On one side, you have the database, right? This is optimized for your nouns, your data objects, your state, the actual information. We usually interact with these nouns using query languages like SQL. But then, on the entirely opposite side, you have your general-purpose application logic. These are your verbs. They execute the transactional instructions using programming languages like JavaScript or Python. These two sides speak totally different languages and live in completely different conceptual spaces. And you know this separation? It causes a massive headache that we call the object-relational impedance mismatch. Because the nouns and verbs are separated, developers are essentially forced to build these massive, clunky translation layers just to get them to talk to each other. You need heavy driver libraries. You have to deal with parsing overhead. And honestly, worst of all, you suffer from network and serialization delays because your data and your execution environment are physically sitting on completely separate runtime nodes. It's just incredibly inefficient. Which brings us to part 2, the June 2020 Spark. What if you could put those nouns and verbs right next to each other in cohesive sentences? Let's rewind to the R&D phase of C3DB in the summer of 2020. This is literally the exact moment the foundation of code data locality was established. It happened during a pivotal, documented email exchange between legal scholar and researcher Kyle Smith and Nolan Buys over at the research organization Metax. Smith was basically trying to articulate a completely unified architecture. And the absolute crucial point comes from the seemingly innocent sentence in Smith's June 19th email. He wrote, "I'll try to show how the code and runtime tree reflect each other so a developer can easily jump back and forth between the two types of expressions." Now, in a traditional setup, code and data do not reflect each other at all. They are entirely distinct. But with this one single sentence, Smith completely reimagines the relationship between abstract digital state and physical execution. Let's unpack that in part 3, defining structural isomorphism. Let's look at the massive theoretical implications hidden in that one idea about the code and the runtime tree. What Smith was actually defining to Metax is a concept known as structural isomorphism. Essentially, it's the mathematical assertion that the program's code, the verb, and the database's data, the noun, aren't just living in the same house, they are structurally identical. And because they're the same, they are capable of executing in the exact same recursive path. This entirely resolves that impedance mismatch we just talked about by merging the application and database layers into one single self-evolving runtime kernel. So how does this actually work in practice? Well, HSDB uses JavaScript as a single homogeneous language for both sides of the equation. Because the execution path and the data retrieval path become the exact same thing, that high-friction translation layer we see in traditional systems, it's eliminated entirely. Gone. You aren't translating between SQL and JavaScript anymore. You are just executing. Moving on to part 4, the math of isomorphism. Saying the code and data are the same is one thing, but proving it mathematically is a whole different ballgame. The deep foundation making this possible is a really fascinating mathematical framework referred to as Pythagorean metal. Instead of treating a database as this static state machine that just sits there waiting for you to query it, it models data and execution as a non-halting, self-reproducing automaton. Think of it more like a continuous geometric engine. And it literally boils down to a unique coordinate formula. Without getting too far into the weeds here, this formula uses classical Euclidean geometry. specifically treating the diagonal of a right triangle as a physical ideal problem to generate an infinite stack of unique coordinates. So instead of standard loop rounds, it uses this abstraction to generate unique input and output data, well, infinitely.
So what's the so what here? Why does this math actually matter? Well, traditional databases guarantee consistency using physical hardware structures, like disk journals or append-only B trees. HSDB throws that whole concept out the window. Because every coordinate is a deterministic step along an infinite geometric number line, consistency is guaranteed by pure math. If a state is lost, it's no big deal. It can simply be mathematically rederived on demand. The state transition is just a scale-symmetric iteration.
Which brings us to our final section, Part 5, Echoes from the Past. Because, as it turns out, this isn't an entirely new dream. While the math of HSDB was a massive modern breakthrough in 2020, the desire for node-encapsulated execution goes way back. I mean, look at 1966. MUMPS was created at Massachusetts General Hospital. It was basically the very first NoSQL database, featuring a tightly integrated programming language where database nodes and variables used the exact same syntax. Then jump to the 1970s, where Roger Schenck and Robert Abelson were developing AI scripts using semantic hierarchies to simulate human reasoning. These historical attempts to unify logic and state directly pave the way for Smith's modern patent filing. But here is a wild twist you almost never see in software engineering. Kyle Smith actually had a background in music copyright law and royalty management, and he brought that exact perspective into the architecture. He didn't view code just as functional instructions. He viewed structurally isomorphic code as a dynamic, creative asset, just like a musical composition. He filed the HSDB patent not to lock the software away in a corporate vault, but to create a legal framework to enforce attribution. It protects developers, ensuring they receive open-source royalties the exact same way songwriters get paid for their hits.
Which leaves us with one final, kind of mind-bending question for today's explainer. We've seen the spark in 2020, the fractal math, the historical journey. But if the code and the data are mathematically the exact same thing, if the nouns and verbs are perfectly unified, when you completely erase that boundary, where does the database end and the application actually begin? I'll let you chew on that. Thanks for joining me for part 1 of this series, and I'll catch you in the next explainer.